Good morning, Americans. Good afternoon, Europeans. Happy tomorrow, Australians. Either way, happy Tuesday, or I guess Wednesday if you're in Australia. Happy to be here. This is our first session today of three. We actually have three sessions going on the Believe in Serverless community today. And this morning, I am joined by Anais Dotis Georgiou. Did I nail it? I nailed your name,
Yes,
right?
perfect. Yeah, thank you.
Yes, yes. From Influx. Now, today, this is a session along our data theme for September. We're talking about all things data. And today we're going to be talking about time series, which is Influx's wheelhouse. But I'm not going to put words in your mouth, Anais. I'm going to let you say all the words and let me not make a fool of myself. So I'm going to go ahead and bring up your presentation, and I'm just going to let you take it from here. Really happy to have you. Anybody watching, if you have any questions along the way, just put a comment in and we will address them as they pop up. So no need to hold your questions to the end. I'll pop in and ask your question for you. So without further ado, Anais, again, thank you for being here and take it away.
Well, thank you so much for having me. I'm excited to be here and share a little bit about InfluxDB, building some data pipelines, and doing some kind of anomaly detection with it. So let's get started. For today's agenda, we'll kind of be starting with what is data plumbing and how does this relate to event streaming and time series databases. Then we'll create a scenario, an imaginary scenario to kind of drive some learning because context always helps. And then we'll try and solve this problem. And the way that we'll solve this problem is by deploying HiveMQ as our MQTT broker, Quix, which is a streaming platform, and InfluxDB, which is a time series database to solve the problem. And I'll share what the problem is, of course, too. And then the next step is kind of just to share some open source code with you and ways that you can get involved with the community, where you can ask questions, resources for learning how to do all of this yourself so that you have a place to start. So my name is Anais Dotis Georgiou, and I'm a developer advocate at InfluxData. And for those of you who aren't familiar with what developer advocacy is, basically it's someone who represents the company to the community and vice versa. So I do that through creating technical tutorials and then giving presentations like this one here. And if you want to connect with me on LinkedIn, I always look forward to that. If you have any specific questions, you're welcome to reach out to me there. But I also highly recommend that you join the Influx community Slack and forums, just because that's where I spend the majority of my time answering questions. So if you have any questions about this webinar, time series databases in general, or anything to do with forecasting or anomaly detection, please reach out to me. I'm just always Anais. There's very few Anaises, so it's easy to message me or tag me on Slack or forums and get additional help. So what are data pipelines? Well, if you're familiar with Kafka, then you're familiar with the source and sink model. Basically, information is generated from, in this case, we'll focus on IoT and we'll say that it's generated from a sensor, but it could also be generated from an application or log, and it needs to make its way to where it needs to be consumed. And that could be other applications, that could be end users, that could be something like a PID controller, an actuator, and et cetera. So when you have that data in a pipeline, you're normally going to need to do certain things to it. That could be like normalizing it or transforming it or changing protocols or standardizing protocols in flight so that you can consolidate all your information appropriately in one place and leverage it as needed to actually act on it. So today we'll talk about how we can use HiveMQ for that pipe. So what is HiveMQ? HiveMQ is an MQTT broker, and it works on a pub sub models like any other MQTT broker, and it allows you to take information as messages to a topic that can either be ephemeral, persistent, or shared among other consumers and producers. And so when you post data to that topic, other devices that subscribe to that topic can then access that data and write it to other databases like InfluxDB, for example. And so in order to understand what InfluxDB is, what it's all about, you need to understand what time series data is. And so time series data is any data that has a timestamp associated with it. So it's probably exactly what you thought it was. And when we think of this in the industrial IoT scenario or IoT scenario, we're really thinking about time series data being produced from sensors or PLCs. So we can think of data like flow rate, concentration, light, temperature, pressure, wind speed. These are all examples of sensors and types of time series data. However, probably the most common example of time series data that exists is stock market data. And when we think about stock market data, it just really helps illustrate how time series data is unique in that a single stock value is not that interesting, unlike a relational database or data that you'd put into a relational database where a single row could be a value. Instead, with time series database, the trend of that data over time is what's interesting for us because it helps us determine whether or not we need to buy or sell. In an industrial IoT use case, it helps us determine whether or not our manufacturing and chemical engineering processes are proceeding as we expect, and actually helping us produce the products that we want to be. So, in general, with time series data, we're looking at our data over time, and that means that our time series databases need to not only accommodate time series data, but also index on time so that everything is presented to us in time-ordered fashion. And that brings me to the types of time series data that exist. We generally think of time series data existing as two main categories, but you could also include kind of a third category, which would be logs and traces. But the main two to think of are metrics and events. And the way that we define each one respectively is that metrics are any time series data that is given at a regular interval. So if we're polling a machine or a sensor for some data, think about, let's say, a vibration sensor, and we're getting a vibration reading per second from an accelerometer, that would be an example of a metric. Events, however, are unpredictable, and we can't derive when an event will occur, but we can still store them all the same. So if we think about a machine fault alert, for example, we don't know when a machine fault will occur, but we can still store it when it does. One interesting thing when we think about events and metrics and how they relate together, though, is that any event can be transformed into a metric through aggregation. So if we did a daily count of how many machine faults that we have during the day, then this metric will either be 0 or greater, and we'll get at least one reading a day. And in this way, we've converted that irregular time series data into a regular data. And this is something that time series like databases like InfluxDB are also very good at doing. And any time that you perform any aggregation on your raw time series data and convert it to an aggregated lower precision aggregate, that's known as materializing your data, creating a materialized view of your data, or downsampling your data. So what is a time series database? A time series database basically has 4 components or pillars. The first is that, of course, it can ingest timestamp data, time series data, and it allows you to query that data in time order. The second is that it accommodates really high write throughput. So in most cases of high volume or batch data or real-time streams, for time series specifically, we're looking at really, really high write throughput. So if we go back to thinking of a vibration sensor, an industrial vibration sensor produces up to anywhere from 1 to 10 kilohertz of data per second. So that's equivalent to 10,000 points per second. If we were monitoring multiple machines that require multiple vibration centers, you can quickly see how we would be ingesting tens of thousands of points alone just from the vibration sensors alone. So if we had multiple machines and we're also looking at things like pressure, temperature, etc., you can see how quickly that would increase your write throughput. And one benefit to using MQTT is that we can connect hundreds of thousands of devices all at the same time and write those to different topics in parallel. And a time series database has to be able to accommodate that type of throughput of both different sensors, all writing data at one time to the same location. Yeah. And the other thing that we need to think about for time series database is efficient queries, because if we can accommodate a really high write throughput, but similarly we weren't able to query effectively and efficiently, well, then that doesn't really do us much good. So we need to be able to perform aggregations over time. We need to be able to accommodate for really fast scans over the data as well. It's very common, especially in IoT use cases, where you're looking at global minimum and maximum values. And so that means that you need to be able to scan across all of your data all at one time to get those. And last but not least, similar to pretty much every other database as well, we're looking at scalability and performance. So you need to be able to scale horizontally to handle this increased load. And yeah, that's all I'll say on that. But let's look at InfluxDB 3.0. So InfluxDB 3.0 is built on the Apache ecosystem because we really wanted to contribute and be a part of open architecture and the open data format. So we support and continue to contribute to Apache Arrow, Apache Data Fusion, and Parquet. And this is a complete rewrite of previous versions of InfluxDB. And the reason why we built InfluxDB 3.0 on the Apache ecosystem is to really focus on interoperability and allowing users to leverage the tools that they already use for things like data processing tasks, for visualization, for querying, etc. So Data Fusion is what we use for our query execution framework, and it's responsible for things like pruning and pushdowns. It also is what allows us to query InfluxDB 3.0 with both SQL and InfluxQL. And InfluxQL is just a SQL-like query language that's specific to InfluxDB. Then we have Apache Arrow, and that's what we use for our in-memory columnar data format. And then Parquet is our durable file format, and it's also columnar. And we switched to row-based format to columnar in 3.0, and part of this reason is basically because time series is really well suited to columnar format. So when we think about what a table might look like in InfluxDB 3.0, we would have, our temperature values, our pressure values in another column, and then maybe we might have some other columns that have metadata about the IoT use case that we are using InfluxDB for. So maybe it's like location or sensor ID, etc. But you can imagine if we want to be able to query the temperature values and find the maximum temperature values for millions of points, it's a lot more work to go row by row in order to extract every temperature value than it is to just scan that singular temperature column for that maximum value. Additionally, time series data is unique in that when you are monitoring a physical environment, frequently that physical environment doesn't change. So specifically with temperature, in an industrial IoT scenario, oftentimes the goal is to maintain a constant temperature. We have control over these environments, and that's why we are also monitoring them. And as a result, that enables when you store things columnarly and you have like multiple rows that are the same with the same value in that one column, then that provides opportunities for really cheap compression and things like dictionary encoding that help just increase the performance both of write and query. So that's kind of InfluxDB 3.0 in a nutshell. But today we're going to be focusing on how we can use HiveMQ to collect all of our data from a variety of different sensors. Then we're going to aggregate that data in our pipeline, and we'll use a sink to tap into the data from HiveMQ and then write that data directly to InfluxDB. We'll also showcase Quix, which has support directly for InfluxDB, HiveMQ, and MQTT. And what we'll do is we'll combine all of these technologies into one architecture and create this data pipeline. And in this example, we'll see how we can ingest data from HiveMQ to InfluxDB, and then how we can perform some data processing and enrichment tasks so that we can do things like anomaly detection and incorporate machine learning. There we go. So specifically, we'll also talk about how we can use Quix. So Quix is built on Kafka. So if you're familiar with Kafka, then you'd understand how the plumbing under the hood works with Quix, but basically it's an interface for Kafka. So you don't really have to know how to actually use Kafka in order to use Quix. And you can choose to either use pre-canned plugins from their code samples libraries or modify and build your own Kafka pipeline using Quix. And it's all Pythonic, so it makes it really easy for anyone, especially in the data science space, to kind of create data engineering and data pipelining solutions with Quix. And it allows you to not only build these pipelines, but also deploy and monitor them as well. So what kind of problems can we solve using HiveMQ, Quix, InfluxDB, and HuggingFace? And I'll talk more about what HuggingFace is in a second in case you're not familiar with it. But let's contextualize all of this technology within a real world kind of example. So when we're looking at IoT, there's a ton of different problems that we could monitor. That could be from the actual physical space in industrial IoT, the actual mechanics of the machines, but sometimes it could also be looking at applications that help run some of the logic behind the IoT controlling. Whether that's like the control systems themselves or related to the operators. But ideally, we automate the solutions and the monitoring of both of these spaces to reduce error and ultimately reduce downtime of whatever industrial IoT use case we have. So let's imagine the following scenario. We have a packing company and it's having some issues. We don't really know what the root cause is, but we're getting a lot of errors and we don't know why a machine is failing, and we don't know how to identify what's causing the failure. But when it's running normally, we can see that the data exhibits a really strong cyclical and seasonal pattern, and the data is easily identifiable. So it has a very predictive pattern, which paves the way for creating really clean anomaly detection solutions. However, when it starts to break down, it exhibits a different known pattern. So the question becomes, how can we use HiveMQ, MQTT, and InfluxDB to automate identifying and flagging these anomalies so that we can ask an operator on the ground floor to address the issue and kind of help fix a problem? So here's a complete data pipeline architecture drawing for how we will solve this problem today. So basically, in this hypothetical problem, we have 3 robot arms that are packing robots, and these robots are synced to our HiveMQ broker, and then we use the Quix MQTT client to ingest that data in real time and then feed it to our Quix destination InfluxDB plugin. And hopefully you didn't hear that alarm. But then we're going to write that data to a table within InfluxDB called machine data. Then we're going to pull that data back out with a Quix InfluxDB source plugin. And then we're going to apply a machine learning model that we are importing from HuggingFace to actually detect the anomalies. Then when we find those anomalies, we're going to use the sync plugin from Quix to write those ML results back to a table called ML results within InfluxDB. And last but not least, we can then visualize those ML results in Grafana and then use something like Grafana for the actual alerting, so that an operator can act on those anomalies. So for this demo, we're going to be using a robot machine simulator. This is just built in Python, and just for completeness sake, I wanted to kind of take you through how this was built. So the robots go through 3 steps. They create the machine, and then they create the HiveMQ connection, and then they write the following JSON payload to a topic. So the simulator spins up a thread per request per machine, and each has its own independent connection to HiveMQ. And this is what the JSON metadata payload looks like. So we'll also include a data payload as well. And you can see that the metadata payload has some things like which machine ID it's from, a barcode, and provider. One thing to note as well is that if you had additional data related to the robot and the machines, like some relational data, it's important to keep in mind that InfluxDB is a time series database and not a relational database. So if that's the case, you would want to store, complex relational data in a relational database and use something like the machine ID to join data in another ETL tool or something like Snowflake, for example. Okay, but that being said, we also have the data portion of this JSON payload, and that includes data about our robot, things like temperature, load, power, and vibration. And one other thing to note is that each robot writes to a child topic underneath the parent topic that's called machine. And Oh, this is a duplicate slide. My apologies. There we go. So this is what the code looks like under the hood. So this is just a quick kind of crash course on how you connect to HiveMQ. But basically, there's a Python class for spinning up an MQTT publisher. And then you can set up an insecure connection to HiveMQ's public broker. And that's just a great way for testing your client and testing HiveMQ. And that's just worth knowing. But otherwise, you can set up an MQTT client and pass in public broker credentials or private broker credentials, depending on whether or not you're testing. And then to connect to HiveMQ Cloud, you also need to set up authentication because it is natively secure. And once you do that, then you can set up an SSL certificate and a username and password. And this is also provided to you during the Python onboarding within HiveMQ Cloud, so it makes it really easy. And then last but not least, we construct our topic and send our data with the client.publish method. So at this point, we are writing data to HiveMQ. And so now the question is, how do we use Quix to tap into this data stream? And the way that we do that is through the MQTT subscriber plugin. So we're going to subscribe to all 3 child topics with a wildcard. And so we can see machine/wildcard there on the left. And we're going to bring in that JSON payload into Quix. And then we parse that payload, and then we write that to a Quix stream, which is really just a Kafka stream under the hood, but you don't have to worry about that because the interface abstracts all of your interactions with Kafka. So you can just focus on ETL tasks and data science tasks. So yeah, you don't have to worry about anything like Kafka partitioning, etc. And from there, we parse that JSON payload and write this directly into the QuickStream topic. And then we can leverage all sorts of source plugins, all sorts of transformer plugins and destination plugins within Quix so that we can really enrich our data as we need. Quix also lets you monitor your CPU and logs from HiveMQ. And so that just kind of makes observability into your pipeline a little bit easier, and kind of you have this one-stop solution within Quix for that. So let's talk about some of additionally the real-world challenges associated with data science, specifically in IoT. So in an ideal world, we would have our machines, maybe machine 1 on the top and machine 3 at the bottom, that are all generating some data. And when we have anomalies, it would look drastically different. And maybe our data would look so drastically different with an anomaly that we could just do something like a simple threshold and easily detect anomalies in our data. Wouldn't that be nice? Well, unfortunately, in the real world, that's not usually the case. Oftentimes, our regular data exhibits some sort of seasonality and standard deviation, and our anomalous data also exhibits that same seasonality and same standard deviation. So we can't use statistical methods to identify our anomalies, and instead we have to do something a little bit more sophisticated than that. So in those instances, we actually need to be able to learn what the shape of our normal data looks like in order to detect our anomalies. And the way that we're going to be doing that today is by leveraging an artificial neural network, or ANN, specifically an autoencoder. So an autoencoder is an unsupervised machine learning method, and essentially what it tries to do is learn patterns without labels or formats or inputs from humans, from me. And one cool thing about autoencoders is that they were actually originally designed for image compression, but then people found out that they work really, really well for time series anomaly detection because they're very good at identifying and learning the shapes of the data. And so if we imagine for a second that an autoencoder is, the job of it is to learn a dance, not time series. I like to think of it in the context of a dance because I used to be a dancer, but also because when we think about time series data is really just learning shapes, and learning a dance is really just learning shapes. So basically the way that autoencoders work is that they have this input layer, and the input layer is basically like telling the robot that it will learn a dance, and this dance will be made out of specific basic steps. And then we have a sequence layer, and the sequence layer helps the robot understand that if we were to imagine what it might be like to prepare the sequence of dance steps to be learned over a certain number of beats or a certain number of counts. Then we have the LSTM layer, and this is like the robot's memory. So as the robot watches the dance, it uses these layers to remember the dance in sequences, and then it focuses on remembering really the main parts of the dance, like what parts were dramatic, what parts were slow and fast, etc. And then there's other LSTM layers that try to remember key movements that define the dance's style as well. And then we have the encoding layer, and this is kind of the layer where the dance moves are encoded in a simpler form. And so it's kind of a compressed memory of the dance. And this is kind of what you do when you learn a dance yourself. I don't know if you've ever tried to learn a dance, but you first focus, when you first learn it, you kind of see what it looks like all together, the main overarching themes. Then you focus on snapshots of the dance. And then, during that encoding layer, that's when you're really just remembering key moments, and those key moments help prompt you to understand what comes next. Then we have a repeat vector layer, and this helps the robot get ready to actually recreate the dance. And this is kind of like what is considered the core memory of the autoencoder. Then we have the decoding LSTM layer, and this is basically where you kind of recall the full dance from these core memories. And then last but not least, we have a time distributed dense layer, and this is where the robot kind of refines each move and ensures that each dance step is as sharp and it matches the original choreography or the original time series as closely as possible. So it's very kind of intuitive because that's kind of how our brains work as well. But that's essentially how autoencoders work in the abstract. And so how are we using this to detect anomalies? Well, essentially what we'll be doing is we'll be using the autoencoder to actually forecast some values based off of what we expect the robot to be doing, based off of what we expect the time series data to look like. And then we will be calculating a mean squared error between the actual data and our forecasted data that's generated by the autoencoder. And this MSE will represent a reconstruction error, which is a measure of how well the autoencoder actually recreated our input data. And so when we have a deviation from normal behavior, we'll get a higher MSE, and then that's how we know that we have an anomaly. And so I also wanted to talk about some real-world challenges from an operational standpoint as well. So one big thing to think about is kind of the divide between data engineers and data scientists, because you can have a data scientist that trains a model perfectly on some sample data, leverages Jupyter notebooks and Keras, for example, to train this autoencoder. But then you have people in the MLOps team or the data engineering team that are trying to take this miracle pill of a solution that the data scientists have created. And it works really well in their controlled specific environment, but they have the job of building it into production and using it in everyday life. And so this is oftentimes where a bottleneck occurs, where we have these great machine learning models, but we don't know how to make them ready in production. And that's where HuggingFace comes in. So for those of you who aren't familiar, HuggingFace is kind of like GitHub on steroids. It's a central repository for storing, evaluating, and deploying models along with their data sets. So you can upload a model like we've done here, and then use their API, which is a developer-friendly way of deploying any new model that you've trained into your data pipeline. And Quix also has an integrated native plugin with HuggingFace so that your data scientists can stay in their realm and leverage notebooks as they're accustomed to doing. Then they push their models to HuggingFace, and then your data engineers can incorporate those models and deploy them with incremental testing as they need. So the cool thing about this demo is that you can generate anomalies in real time, and then the autoencoder will catch those anomalies as well in real time. And it also includes a Grafana visualization. And so I encourage you to take some time to run this demo yourself in your free time. The only thing that you need is an InfluxDB cloud account and a Quix account. And so when you do run it yourself, then you can see that this is what the Quix pipeline ends up looking like. And you can dive into any specific component in that pipeline and look at things like CPU usage as well as logs. And that's really helpful for debugging your pipeline and in general, just observing and monitoring your pipeline. And so this is what kind of our machine data looks like. You can see that it looks regular here for 2 machines, and then towards the end, we are presented with some anomalous data as well. And so at that point, we're able to flag those anomalies, and the number of anomalous incidents or events that we have has increased from 60 to 92. And this is just an example of what the Grafana dashboard looks like for this particular example or demo. So kind of just to wrap up here, just to summarize. So this is just an example of how we can use Quix, InfluxDB, and HiveMQ and HuggingFace to operationalize anomaly detection in the industrial IoT space. And the cool thing about this stack specifically is that while obviously it just leverages 3 machines, from a machine generator, we could easily scale this to operate on thousands of robots. So the pipeline here is robust enough to easily be scaled out for an actual IoT use case. And I also wanted to talk about kind of where we could go next with this project. So some things that we could think about is maybe also imagine putting another labeling algorithm and actually label the type of anomalies that we are getting. And so we can actually, off the cuff, be able to identify, is this machine fault because we have bad bearings? Is it because of a shaky belt? Is it because of an unexpected load? Etc. And then actually provide the operators with that information in real time so they can understand what the condition of the machine is. And then, of course, everyone's really excited about LLMs right now, so naturally want to take a moment to talk about how we could integrate them. And as they get better and faster, we could think about how we could use them to do things like automate protocol conversion, or maybe even translate machine language into human readable language. And you can imagine that we could maybe entirely replace a Grafana dashboard because we could use LLMs to read that Grafana dashboard and tell us in human language what's wrong with the machine. We could also use AI to pass on expert knowledge. So we could monitor how the operators and experts themselves are troubleshooting problems based off of this anomaly detection solution that we've created today, and then create models based off of their domain knowledge in those specific areas and pass this knowledge down to new technicians and offer prompts to help them solve the problems. They could automate the information that they're being supplied with. So they could be provided with particular documentation or specific protocols to assist them in identifying the root cause problem and performing root cause analysis, and also how to solve the problem. And so that leads us to thinking to eventually about maybe having self-defined digital twins, where those twins are making connections between the machines, the sensors, and applications, and also creating solutions to proactively monitor and solve the problems that are existing on the factory floor. So you could imagine being able to walk into a factory floor and ask a machine directly, "How are you doing?" And it just tells you how it's doing. And so you could be a machine floor doctor instead. What are some next steps? Some next steps include trying this project out for yourself. I recommend going to the Influx community organization, and if you search for Quix anomaly detection example, you can find this, as well as if you search for saving the holidays, you can find another Quix example as well. And in general, the Influx community organization is a really great resource for anyone learning InfluxDB or trying to leverage InfluxDB. It contains a whole bunch of different examples for how to use InfluxDB with a variety of different tech stacks. So like a project I worked on recently was using Kafka and Faust instead to build a CSTR, or a continuous stirred tank batch reactor, and an accompanying PID controller to kind of show a chemical engineering specific use case for how to leverage those technologies with InfluxDB. We have examples for how to use MQTT with Telegraph, and Telegraph is InfluxData's collection agent for metric and events. Actually, in general, I just want to give a quick plug for Telegraph. Maybe I'll go back to this slide. Well, it doesn't show Telegraph here, but Telegraph, yeah, like I said, it's our collection agent for metrics and events, and it's plugin driven, configurable through a single TOML configuration file, and there's over 200 input plugins. It's also database agnostic, so if you have the desire of writing data to a particular source that's time series, and you need to basically get data from a bunch of different sources and then deserialize and serialize them into one unified data format so you can ingest them into whatever your destination is. I highly recommend using Telegraph for that. It's a very lightweight agent. It also has a whole suite of execd plugins, which make Telegraph extensible in any language. So you could just, create a Python script to get data from a variety of different sources. It both pulls and pushes data. And what else is cool about Telegraph? Oh yeah, you can also reduce the binary size, which is really useful if you're sidecarring it, for example. And it has all the buffering and caching capabilities that you would expect a data collector to have. So yeah, so try it out for yourself. Also, just in general, look at the Influx community organization as a whole, because like I said, it has so many different examples, has examples for a variety of different data sets, a variety of different tech stacks, and also all of our client libraries are maintained there as well for V3. So yeah, go ahead and check that resource out. And then in general, I want to invite you to join the InfluxDB community. So you can sign up for a free cloud trial at influxdata.com. And there's also InfluxDB University, which offers free live and self-paced training on a variety of InfluxDB topics. So if that's your preferred way of learning, that's a great resource. You can also earn digital badges with that and display them on your LinkedIn for certain courses. Then we also have our community Slack at influxcommunity.slack.com. We also have our forums at community.influxdata.com. And I also want to leave room for any questions. So thank you so much, everyone, for joining today. And yeah, let's see what questions we might have. You're on mute, I believe.
Wanted to make sure I didn't make any noise when I was off camera. Thank you, though. That was really good. I have one question, a real brain teaser from Daryl during the middle of the session. Let me bring that up. So he asked, what does InfluxDB offer compared to TimeStream on AWS? It's really a two-part question. And does InfluxDB serverless have a fixed monthly cost to use other than the cost of storage of data that you've already ingested?
Yes. So AWS TimeStream, it is closed sourced, and InfluxDB does have an MIT open source. So that's one thing to know. Also, AWS TimeStream is now serving InfluxDB v2 under the hood as well. So it depends kind of what version you're using, but it doesn't offer v3 presently. So if you are using serverless, for example, then you are using v3, and then you get access to all of the features that v3 has to offer. You can query with SQL directly. You have interoperability with a lot of other tools, with Iceberg support coming shortly. There's also plans to eventually create a data processing engine within Python. There's some ways to handle automatic scaling of certain resources within InfluxDB with v3. And then, access to things like ODBC and JDCB drivers that allow you to have connectivity with other BI and visualization tools like Tableau, Apache Superset, and Power BI coming soon. So I think some of the main advantages are just the interoperability that InfluxDB offers. AWS isn't known for really being flexible and keeping you out of vendor lock-in, and that's one of the main problems that we're trying to solve with InfluxDB v3, because we recognize the need for users to be able to pull their time series data out and leverage it alongside other data, and create sophisticated machine learning tasks or analytics tasks so they can actually do something with their time series data.
And then part 2 of the question is there a fixed cost with InfluxDB serverless in addition to the pay for what you use pieces?
Yeah, and let me give you all of the pricing information really quickly too. So you only pay for what you use with serverless. That is only pay as you go. But let me share that. I'll share that in the private chat with you, and then you can share it wherever
Sure. Yep.
you want to.
Here you go, everybody. So just send out the pricing docs. And for those of you that can't see it, I don't think this streams through Twitter or LinkedIn. So I'm just going to share it on the screen here real quick. influxdata.com/influxdb-pricing. That's where you go to find that. Okay, thank you for that question, Daryl, or those 2 questions. That was a good one. And then Anais, I just have one other more generic question about time series in general, and that's like what other industry? This was a really good use case, real practical one in the robotics and the manufacturing side of it. What other use cases are just home runs for time series data?
Yeah, for sure. I mean, so I think when we think about like where we see time series data being produced, we see it being produced from the physical world and then the virtual world. So other use cases include DevOps monitoring, whether or not you're monitoring the availability of third-party endpoints or CI/CD. That's a huge wealth of time series data, or containers or network monitoring. We also see applications in fintech. Um, we also see applications in gaming as well, where we're monitoring, gaming stats and user behavior, and application monitoring in general. And I think those are probably the main ones. But we also see also in agricultural, and I mean that's kind of alongside IoT and industrial IoT. Just renewable energy is a huge source for InfluxDB as well. We have a lot of customers in that space, either monitoring their solar panels, their batteries, their wind farms. But we also get community users too. I love highlighting also what community users use InfluxDB for, which just spans anything from I've had one person monitor the chlorine levels in their pool and then automatically fill their pool with more chlorine, making their like own personal built kind of controller for that. I've seen people monitor endangered hawks and track kind of their patterns with InfluxDB in the community. I've had people monitor their barbecue and their grilling so that they only get alerts when the temperature reaches a certain amount and they have to go baby whatever they're grilling. And then we also have cool use cases too. CERN used InfluxDB to monitor their particle accelerators. So yeah, because it stores up to nanosecond precision. So we really see like a really wide range of use cases.
That makes me wonder, like, what's it not good for?
I would say
That might be a
relational
silly question
data.
to ask, but it sounds like
Yeah,
everything you can use it for.
yeah, relational data. Yeah.
Okay, yeah, yep,
Mhm.
that makes sense.
And we're diving into supporting logs, traces, and spans as well. And I think that's a big feature of InfluxDB v3 because previously there were some issues with cardinality, but now because we're built on columnar and the Apache ecosystem, we can handle unlimited cardinality, and our like write throughput increased like by 45%. And you can see benchmarks if you look them up online. So
Wow,
or not
amazing.
45%, 45 times. So
Oh,
2 zeros. Yeah, yeah.
that's way better.
Yeah,
Oh my
yeah.
goodness.
Yeah. So yeah, it's wild. And so yeah, that makes that whole having access to ingesting that type of data like opens up a whole new world for us. Yeah.
Yeah, definitely. All right. Well, that's our time. For anybody that might have any follow-up questions after the fact, what's the best way to get a hold of you or to get their questions answered?
Yeah, please, please, please join the Influx community Slack or the forums, and either message me or tag me. I'm always Anais on either one. So yeah, please do that and reach out there. Love to answer any questions you have.
Okay. Well, thank you very much. Super informative session. Loved it. And we will talk to you later. Thank you again, Anais. This was great.
Thank you.